everybody, Jason here from Murideo. Welcome to today's webcast with one of my favorite people to talk to, Mr. Jeff Boccaccio from DPL Labs. Jeff, how's it going?
Hey, it's going real good. Florida's still good now. It's nice and warm.
I was gonna say, man, like we've been great for a couple of months, and I don't know about you guys on your coast. By the way, Jeff and I are both in Florida, just opposite coast, but um, the humidity really rolled in yesterday. It was like fine up until yesterday. It got really gross over
Yeah,
here.
you're right. But boy, that the cold went away real quick, and it got 2 weeks ago. We got to
Yeah,
85, and
yeah.
we've been sailing ever since. So it's been really nice.
There was a
Um,
there was a meme I had shared with a couple friends, and it said like Florida winter, and it was like February 3rd to February 8th. It was like RIP. Like it was like that was kind of it. So
yeah, I know, but I said, I mean, it'd be nice to get a little cooler. I had it for 2 days. I said, okay, enough.
enough, yeah.
Okay, we had it. That's enough.
You know
So
the Floridians are cold when we close our windows when it's 60. I had the windows open for a little while, but it just got too cold. But
I
hey,
know, I know.
that's Florida for you. So I wanted to get with you today. Just there's so much going on right now with HDMI cables, and it was always an interesting thing to me, like when we do transition from one format to the next or one bandwidth to the next, what's actually happening. And in these transitional periods like what we're going through right now, and one of the reasons I wanted to have you on is because there's a gazillion different HDMI cables out there, and we've seen really good ones, we've seen really bad ones. They all have the same labeling as far as the bandwidth that they can carry and all that good stuff. So what makes a good cable a good cable? And that's really the main topic today.
It's been a main topic for years. I mean, from the beginning, there's always been this big hoopla about cables,
Sure.
and there's a lot of people that say digital is digital and are going to be the
Yeah.
same, and to a certain extent that's true. I mean, it's as long as you have the signal data and the data rate that you're requesting, you should have a perfect picture. There's really no question about it.
Sure.
But there's also other concerns around the interface that are problematic. And of course, in the earlier days, we had tons of problems,
Oh, I can only
and,
imagine.
and we're still having them today. I mean, and every time there's a new revision, there's more features, there's more bandwidth, and of course, the cables have to change for that. And then the
Sure.
changeover is always a joke because nobody knows what they're doing,
Yeah.
or they think they know what they're doing, and they don't know what they're doing. So, and we do a lot of cable testing, as you know.
Sure.
We just now with 2.1 around. It's changed. The equipment had to change. We have to increase our data rates. So now we're operating, I think, at 250 gigs of throughput on the system, even though
Yeah.
we're really only using 12
Yeah. Yeah.
per channel. But still, we have to change it, and we have to automate it because there's so many more tests involved now,
Oh,
and
sure.
so there's so many more features. So and what HDMI has done is they've loaded up with all this stuff, and no one knows. They really don't know the total package and how it works. Um, and they did a lot of good things in there to try to remedy the problem areas
Hmm.
where people were confused and people didn't understand, and quite frankly, we talked about this a week or so ago. It's going to get worse. This is worse.
Yeah.
I mean, it took me some time to just study it, and I could imagine a consumer or an installer having to go out and purchase these products and match them up, and it's a
Yeah.
matchup. And in fact, I grabbed the codes from the HDMI website. They now have codes for the matchup. So remember,
Okay.
before it used to be 4K 60 and make sure you have a color depth of 12, whatever it's going to be, right? And
Hmm.
can your unit do that? So now they've got a series of codes, which makes it even worse.
Yeah.
And they just don't get it. And at least in my opinion, they don't get it. So today
Yeah.
we're going to be talking about a little 2.1. We're going to
Hmm.
talk about what cables, is there a difference and why there's difference.
Right.
And I got a little presentation I'm going to show you on that. It's not
Cool.
too technical. I kept it light. But the first slide I have here, which is the next, okay, how come that's happening?
And real quick too, guys, just a tiny bit of housekeeping here. There's a question box. So as we're going through the presentation, if you have any questions for Jeff or myself, feel free to type those questions in the question box. I'll do my best to get to those as we're going. And we'll leave some time at the end for some questions, of course. And if you are watching this live, there is a slider that you can use in the web interface that we're using, where if you want to make our cameras bigger or the presentation bigger, grab your mouse, click on that slider, move it up and down, and add to your leisure. So cool, there we go. There's all the housekeeping.
Okay. So my first slide here is something that I thought would be kind of fun, and it's HDMI cables. Really, all the same thing. Are they the same thing but different?
Mm-hmm.
Now, the reason why I said that is because when I was in college, I had a professor, a chemistry professor, and these we use equations a lot in chemistry, and only they're chemical equations, and there's ways of making elements and making things with different um, chemicals, and H2SO4, and you can go on and on with equations for this. So he went and did on the chalkboard this equation, and he said, "Now we can do it better if we did it this way." And he did it in a different way. He goes, "Now this would yield X, Y, and Z," and it was really incredible. And I raised my hand, and I said, "I don't quite understand." And he did this all the time to me. And he looked at me. He said, "Boccaccio, it's the same thing but different."
Yeah. Yeah.
And I said, "Yeah." And so when we're talking about this cable thing today, they're the same thing,
Mm-hmm.
but they're different because there are others that have much better attributes than others have, and there's different channels within the interface that
Right.
have to be pretended to. And so I thought it'd be a good idea to go through that, and so people understand that there are really differences, and that
Mm-hmm.
and actually, since we test these products, we actually test them in an analog mode. We don't test them digitally.
Mm.
So we're looking at analog numbers. We're not looking at data. We're not running software through these products.
Right.
We're running, we have a BERT, just like maybe you guys have a BERT. I mean, we have generators and stuff that do it, but it's analog, it's not digital.
Right.
So anyway, that's what we're going to talk about. The same thing, but different. So here's our typical HDMI interface. I did this last time we spoke. And just a quick review on this, because this is where the meat is. And
Real quick, Jeff, sorry
yep.
to interrupt. The screen that we see right now from you still says, I don't know if you switched slides yet. I still have the what cable do you have in your wallet slide.
Oh, oh wow, I've switched slides 3 times already.
Oh, that's okay.
So let's see. Maybe show my screen. What's that? Does that help?
Yeah, I do see now the diagram that you have,
Okay.
but it's not on the main screen. It's like a secondary screen. You had a button in there, I think, that said swap screens. Did that help? Stand by, folks.
Um. Hmm.
Well, I can still see it, and if we want to make it size-wise, let's just turn off our
All right.
cameras.
Well, oh, I see. That's right. We're on the same. Let's turn the cameras off.
Yeah, that'll
Let's
give
do
us
that.
more physical space to see the slides. Okay,
Okay,
cool.
good. So is that better?
I still see your camera, but that's okay. The presentation's nice and big.
Okay, good.
If
We'll
you guys
just
are watching live, if you have any problems seeing it, just let me know and we'll work
yeah.
on it a little bit more, but you should be
Yeah, I
fine.
mean, we've had some problems with this stuff lately.
That's okay.
Anyway, so here's our interface. You see that, right?
Yes, I can see that.
Okay, good. So now we have this is the meat and potatoes of the whole interface. I mean, you've got to have this to make it work.
Right.
And this is 2.0 stuff, but basically we have a power line, we have hotbar detection, we have this thing called DDC, which is I squared C, which is Phillips I squared C protocols.
Yeah.
And that's really the communication channel that gives us all the brains. And then we've got video for D0, 1, and 2, and then we got a clock. And I want you to notice on the clock, it's skinnier. You notice
Yes.
that arrow's skinnier. That's going to bring up an interesting point later on. And we'll get to that later on. So, this is kind of what we're dealing with every day. And so you have to look at what the performance, what performance variables are within cables. I mean, there are performance variables in these things.
Sure.
And one of them, of course, is gauge.
Mm-hmm.
And so when you look at different gauges, the bigger the number, the thinner it is. The
Mm-hmm.
smaller the number, the fatter it is. And you can
Mm-hmm.
see the little arrow on the side saying, better is when you go fat.
Yeah.
So it's good to be fat. You got to be fat cables. The problem with fat is that they get clumsy, they're heavy, you can't bend them, yada
Yeah.
yada yada.
Yeah.
And but that's kind of how the performance works on the gauge, right?
Hmm.
And then of course we also have distance. So distance is a big one because the shorter the distance, the better the performance.
Totally.
But again, we're always looking for long distances, and this is in copper passives. We're not talking about AOCs or opticals. So that's kind of the way that whole thing works. But there are other performance variables that you have to be concerned about, and we see it all the time. And one of them is, are they twisted pair or are they twin X designs? There's a big difference between these two. And twisted pair is what we always use because it does wonderful things with crosstalk,
Hmm.
and it does a great job at that. However, in a twin X design, we typically get much better bandwidth out of that, which means that the shielding has to be better because we're not going to have the crosstalk
Hmm.
characteristics. So each individual differential pair has to be shielded really well. They're both used. Option for me would be twin X for sure, especially since we went to 2.0 for 18G. To get a good 6 gigs, most of the people were using twin X. Now with 12 gigs as the standard for high end, twin X will probably end up being more the standard, at least especially for cables more than say 2 meters, 3 meters.
Could we talk about just real quick, a twisted pair? I think we all know that, but what about the twin AX? Well, what's kind of the
Oh,
quick and
I'm
dirty
sorry.
on that? No,
Oh,
that's
I
okay.
should have made a slide for that.
That's all right.
Basically, twisted pairs, you take a differential pair. Remember, these are differential.
Right.
So they're not single-ended. So there's actually 2 hot wires. There's a
Hmm.
plus and a minus, and then they have a
Hmm.
common ground.
Hmm.
And so in twisted pair, they twist these, okay, and they twist them and they twist them all the way through the cable. And they do that by twisting them, eliminates a lot of the crosstalk issues. Actually, Bell Telephone figured that out about 100 years ago.
Yeah. Right. Yeah.
And but on a twin X, they actually flow. Both wires flow in parallel with each other,
Hmm.
where they're literally like Siamese twins.
Yeah.
Uh, and in most cases, they're within the same jacket,
Hmm.
but they're separately shielded between the two for a bit of crosstalk, and they shoot those things right through. Well, of course, immediately we're going to gain on the distance side because on the twisted pair, they're always going to be longer than the twin X.
Hmm.
Not a lot longer, but they're going to be a little longer, so
Sure.
you
Makes
have to
sense.
add that into it. So that's basically the difference between the mechanics of the twin X.
Cool.
And then, of course, there's a manufacturing ability, and that's critical, because especially as you move into higher bandwidths, soldering is important. A lot of today's stuff is automated, so that's getting it
Hmm.
better. But you put too much solder on, you begin to start building stubs.
Yeah.
Uh, stubs are impedance matching devices, and a large amount of solder will create a stub, and it'll produce sometimes it'll produce a sec out. It'll change the response curve. It's all got to be very carefully done. And if
Hmm.
you've ever been in China and see them do it, these kids, and they sit there with no glasses and they're soldering these things.
Yeah.
It's mind blowing. Mind
Yeah.
blowing. And they still come out very good, by the way. But again, manufacturing is everything. And then, of course, we have the metallurgy, which is okay.
Hmm.
What are you using for metal? And some of that metal could be copper, which is, of course, we use copper most of the time.
Hmm.
And now, if you want to do a little better than that, you can do silver. We've got guys with solid silver. Now that's a teeny
Solid
bit
silver.
overkill. Oh yeah,
Wow.
yeah, really a teeny bit overkill. Because the inner core doesn't need the silver, but people do that, and they're good. They're good.
Mhm.
Just probably a waste of money, but they're good.
It seems like there's
Uh,
a lot of copper, but coated in silver out there.
oh yeah, oh yeah. I'm going to
Yeah.
get to that. So we have gold. We have the guys that like gold. I mean, we got some crazy cables coming in here.
I bet.
I mean, we get all kinds. And so then we get silver over copper, which is what you talked
Oh,
about,
there you
right?
go.
And then we have also gold over kryptonite.
Mm,
Now that's a real good one. I just had to do that.
that's that.
And then of course that takes over the smoke and mirrors.
Yeah.
So it's we got all kinds of good stuff.
There,
So,
there,
but
there are probably a few folks that are going to watch this that are old enough to get the kryptonite Joke.
Yeah. Well, you know what? They can Google it and they can figure out where it came from.
That's true. Yeah.
So let's have some fun with this. Let's not tell them. We're not going to tell them because
Oh
you and
yeah,
I.
no way.
Okay, so that's kind of what it is with performance values of variables. And in today's day, this is a typical manufacturer now.
Hmm.
Actually, that's not typical. This is the only manufacturer. You can see what they're doing here. They now have on their final assembly a complete setup of eye patterns.
Hmm.
And this was not cheap. We helped them put this in there for them. And they wanted to make sure they did the job right. And so now, because of these performances, you're going to see these performances today. But because of the performance issues between all four channels, their operators now, the end user operators you're seeing there, can actually view the four channels right when the thing comes off the line.
Mm,
And then what we did is we built in their limits so that if it hit a certain limit, it'll flag them and say, it's out of limits, dump
right.
it. And they could never do that before because they were using televisions.
Yeah.
And I mean, cut me a break. You're using a television to
Yeah.
do.
And what TV and how tolerant are those inputs and how well are those soldered? That brings
Oh,
in that's a whole other
oh,
thing.
oh, I mean, I could tell you stories about circuit
Oh, I
boards.
bet. I bet. I bet.
So, but anyway, that's what I think that what you're going to see in the future is more of companies like this one
Hmm.
will develop into using higher end final testing procedures. And these guys are way ahead of everybody, this particular
It
company.
it looks like in that picture at least he's got four eye diagrams up there, and if I'm seeing it correctly, it's channel one, channel two, channel three, channel four. So they're literally looking at every single channel at once, right?
Yes, right. In fact,
That's cool.
the system is designed so that the cable goes in, they hit a button, and 10 seconds gives them all the eyes, and it even prints a report for them.
Oh,
So
that's great. That's cool.
yeah, so if the customer wants to say no, I want to put a report in every customer's jacket
Hmm.
on their cable, they could actually print the report, and they get the whole report, and that report can be lengthy.
Oh,
I mean,
sure.
it could be pages long, or they can make it small. But
Hmm.
again, they're so far ahead of everybody. These guys
Yeah,
are just
that's awesome.
these. Yeah, they're good. So when we go back to the interface, basically the two most important things in the non-data side, and I'm sorry, the low-speed data side, is 5 volts, okay,
Hmm.
and DDC. So, and the 5 volts is very easy to understand, and we went through this last time.
Yeah, yeah.
And that is that you got to have some 5 volts, and you have to have the current to back it up. So the current's only about 55 mils max,
Hmm.
and that isn't much. But as you go longer and longer distances, of course, that cable size has to increase
Hmm.
in order to carry a better current. Now we know that by the end of the year, we should start seeing high current, high powered from HDMI.
Hmm.
So the 55 is going to go to, I think, 270 or 300.
That's good
Uh,
for distance.
oh, that'll be great because
Yeah,
it'll solve all the AOC problems.
yeah.
Because they draw too much current and they got to use external supplies to make it work right.
Hmm.
So yeah, so if cable manufacturers in the AOC side are doing their job, they would be beefing up that 5 volt line
Hmm.
because in the future that's going to be able to handle a lot more current. And then of course there's the DDC line. Now this one is critical. In the earlier days of HDMI, this actually was the biggest problem.
Oh,
It
sure.
wasn't it wasn't video. It was
Hmm.
DDC. And there's a good reason for that. And this is kind of what DDC looks like in an oscilloscope
Hmm.
portion. And basically it's a square. It's supposed to be square, but in this case it's round. You can see that.
Yeah.
Let me see. Can you see my mouse in there?
Yes, I can.
Okay. So you see I'm circling this little time.
Right.
Okay. So this time period between here and here is how long it took to get from here to here.
Hmm.
And there's a certain spec for that Philips gives you. And basically this is a low, down here is a low, and up here is a high. And we just load it down on the oscilloscope so we can see it. And then we could take a picture of it and measure it.
Mm.
And that way thereafter, the measurement is what I'm looking for. Now HDMI doesn't do this. They just look at capacitive loading in picofarads.
Hmm.
And it's nowhere near as accurate as this is, nowhere near as fast, and it doesn't work for um, for active cables that have any kind of I2C accelerators in them, which almost all of them do today, when you get past like 15 meters.
Yeah.
So this gives us an opportunity of testing them perfectly. And Philips did a great job with this, but this is what that data line does. Now there's two lines for this. There's a data line, there's a clock line. They both have the same spec. And you see on the left here where the little capacitor over here going to ground. Well, there's a certain amount of capacitance between the data channel and shield.
Sure.
And that's what this is what this curve is showing you.
Okay.
Is what the capacitive loading is. And we want this thing goes vertical as much as possible. So let me give you an idea what that looks like now, because you have to take that under consideration when you think about distance. And we talked about this earlier with gauges and distance. So here's a perfect example. We have here a source. So this is a Blu-ray player, set-top box, whatever you want to call it, right? And then it outputs a data and a clock. That's what it outputs. And it outputs that to a sink on the other side, so that, which is our display. So we have to communicate with that. And it's going to talk. We communicate HDCP, we communicate EDID, and now with status control, we communicate all kinds of other stuff,
Sure.
including error correction. And now with 2.1, it's even worse.
Yeah.
So this is a very important channel. It's got to be good. And this was nothing but headaches in the earlier days. And today it's still giving us headaches, depending on your length and the quality of the wire. But you can see here, and this is a 2 meter run. In 2 meters, we have 0.33 microseconds of speed issues. Now that's not much. The maximum is 1,000. That's after you take away all the loading factors of the test equipment. You're looking at about 1,000. So this is 0.33. It's 1,000 nanos, or 1 micro is what the limit is. So we have some time there. So let's extend it out to say 3 meters, and now it goes up to 0.4. So you can see our DDC numbers are getting worse as we're getting out there, right?
And that's not a little bit of a difference. I mean, 33 to 433 is pretty. Yeah.
We did this with a company's cables, and we had the same size cable all the way out. We made our own, and this is how we made this test. And then so here's another one. Here's I think next one's going to be 5 meters. Now we're up to 0.6. Right? So that's 600 nanoseconds, or 0.6 microseconds. And then the next one up is going to be 7, and now we're at 0.78.
Yeah.
So you can see it's heading south very fast,
very quickly. Yeah.
And again, the gauge has a lot to do with it. So a thinner gauge, this would have been much worse earlier on.
Totally.
So by the time we get to 10 meters, we're at 1.05. We failed. And this happens all the time.
Yeah.
And especially in AOCs and opticals, they're really, really bad because they're so thin.
Yeah.
So they have to use they use a 32 gauge, 30 gauge cable, and it's a real problem. So that the good ones are usually made better, or they're using some form of an accelerator. And the accelerator, of course, guess who makes the accelerator? Philips.
Yeah.
And so that's kind of the picture. What?
And just so everyone's kind of on the same page here, if we're talking about AOC cables, all of this stuff we're talking right now is going over the copper. So just to make sure everybody's kind of on the same page with that.
That's right. This is on copper, yes.
Yeah, I've seen some AOC cables from different a lot of manufacturers, especially where they're really, really thin. So that makes me wonder, well, the fiber is super thin. I mean, that's a given. But if the cable's really, really thin, are they also using a super, super, super high gauge cable also? Or do we go, I mean, I've had this argument with people over the years about, like, everybody's so obsessed with how thin the TV is and how thin the cable is and how thin our phones are. And it's like, guys, I mean, that's cool that it's that thin, but like like, give me better battery life, give me, bigger screen, give me this, give me that. And in this case, it's give me something that works.
Yeah. Like I said, you don't want to mess with this interface. This portion it's really, really critical, and we see it all day long here. It's it's very disappointing, I have to tell you.
Yeah.
I mean, we for the first time we're rejecting more than we're taking in.
And I don't want to give away any specific numbers or anything like that. I don't want to put your kind of business out there, but it's my understanding right now that you are testing, let's just say, a lot of cables.
Yeah, we've gone through this month. We went 600 units.
Oh, see, there you go. There's a number for you. 600 in 1 month.
Yeah, a lot of
And
units.
compared to 10 years ago.
Yeah, I mean, well, 10 years ago we started. We're just about 10 years old. But yeah, it was nothing like 8.
Yeah, yeah,
It was,
yeah, exactly.
so this is back to this waveform, and this is where it breached. And you can see here, right up there, you see the voltage is at 4 volts,
Yep, yep.
and the delta T is the time, and it's
Mhm.
1.05. That fails. So this little puppy is bad juju. We call
Yeah.
this bad juju, and you don't want to have that. And I would say that any AOCs out there that doesn't have some sort of correction in it, or they
Mhm.
didn't take care of business, is like this. And
Yeah.
they're saying, oh no, my AOCs aren't working. AOCs not working. I hear it all the time,
Mhm.
and it's either power or it's I squared C.
Yeah.
Very rarely is it going to be video. Very rarely.
Is
So
is is there something you can think of? I just had this thought off the top of my head, so if it's a dumb idea, just let me know. But is there any kind of test equipment out there? Like the Murideo stuff is more of like a pass fail. Is there any piece of test equipment out there that you can think of that an installer might want to consider if they want to get these real specific numbers? I mean, obviously you're in a big oscilloscope that's probably on a bench somewhere with this one, but are there any small ones you can think of that can give you the same data or no?
you'll never see them up here.
No.
Now for
Yeah.
this, okay, well, I take that back. For this particular test, yeah, you can. I can even recommend a little portable. They're about this big,
Yeah.
and they actually have the ability of doing this test.
Okay, cool.
But they can't do the video. This is only 100 kilohertz.
It's
This is
only,
nothing.
yeah, right, right.
But when you start getting into 12 gigs, it's not going to happen.
Yeah, sure.
You're not even going to get it for a gig.
Hmm.
So it's not gonna. You're better off with a Murideo, only because they have the necessary outputs. The output is pretty much at instrument level.
Right.
And so it's the best way in the field to really to test it.
Cool. Good.
You're never going to get a test lab out in the field. That's not going to
Yeah,
happen.
no way. Yeah. Okay.
Okay, so let's get on with the rest of the interface. Now the rest is of course data lines, right? D0, 1, 2, and then there's our little skinny clock down there. Remember that one,
Hmm.
right? So when you look at video up to 2.0, we're looking at data rates for 720p. Now notice the size of that eye pattern, right?
Yeah,
It's
it's
actually
big.
it's two sinusoidal sine waves, 180 degrees apart. It's basically what it is, and
Hmm.
it's because it's differential. So, but we also saw that same thing at 1080p, didn't
Hmm.
we? But notice it got smaller.
Yes.
So the waveforms are getting tighter and tighter and tighter as we go up in frequency, and
Hmm.
the amplitude drops. It always does. Over a transmission line, as you go in upper and high and data rate, the amplitude is going to drop.
Hmm.
And we need that amplitude. Remember, look at analog here, not digital.
Right.
The amplitude is analog. So if we now look at, here's 4K 60, all right, and that's operating at 18G. Here's 4K 60 at 18G, right? Look how
Hmm.
much smaller it got
Yeah.
and how much tighter it got.
So
Okay,
there's more stuff at a lower amplitude.
more stuff at lower amplitude, and it's only because of the natural characteristics of copper.
Sure.
It's going to roll off. I mean, that's where
Right.
the S. That's how come we do S parameters. So then, if you go back to the interface again, you say, okay, that clock channel down there it's skinny, and the reason why it's skinny is because it doesn't handle anything more than 150 megahertz.
Hmm.
So the cable manufacturers, excuse me, can save money by not putting the heavy gauge in that one channel.
Sure.
They get away from it. But a few things happened. One thing was the um, HEAC came out, and HEAC, which is the Ethernet line, right?
Hmm.
Well, that's full differential. Now,
Right.
its bandwidth is 200 megahertz. So this isn't quite there, but most of the cables that are out there can handle 200 megahertz. Okay, so they have and you have to also remember that one side of the differential pair is a free wire that they left in the system,
Yeah.
pin 14, and then the other side of the differential pair is actually the hot plug wire,
Hmm.
and the hot plug wire has DC on it, so they float it on the DC, which is very easy to do. It's not rocket science. So There's our two differential pairs. So we have to make sure that our HEAC dumb wire and our HEAC hot plug wire is working well. But on the clock, we only need 150 megs. That's all we needed there, right? Well, that's okay, except when we go to 2.1, that clock has been changed.
Right.
There is no more clock. So the clock's now embedded. So now they beefed up the size gauge of that yellow wire to match the bandwidth or the data rates of the rest of the other wires. So now we have 12, 12, 12, 12. That gives us our 48, and we're ready to rock and roll.
So, question for you then, is this the reason why some older cables will work while some won't? Maybe some older cables did have a nice fat cable for the clock channel,
Yeah.
and some older cables stuck with something really small because they were trying to save a buck, which I totally understand and appreciate. But if you have a high quality older cable, this is why it'll still work in the system. Is that fair to say?
That's very true. In fact, it's going to come up in just a minute. You'll see this.
Listen, man,
come
hey.
Up. Well, no, it's good. I'm glad you brought it up. It's great.
I got my crystal ball over here, I guess, today.
Well, okay, if you look at 8K now, that's at 12 gigs. Now we're small. We're really small. So, in other words, and when we're checking these things, 100 mils is their limit mark. Okay. So their limit mark is peak 100 mils. So it's a 10 volt.
Right.
So it's just getting down there. So here's some eye patterns to look at to give you a general idea of what you're faced against. And this channel, we have channel 1 here that looks pretty good. You can see there's a little gray. What happened there? Can I go? I went backwards.
Yeah, I just went
You
backwards.
see this little gray area.
Yeah.
The red area is the actual mask. We don't want to touch that.
Right.
We don't want to touch that. The gray area is the mask margin. And that means you've got margin between the mask itself and the eye itself. And so we're looking for symmetry. We're looking for ISI, which is symbol interference, jitter over here. There's countless things to look for. But if you look at channel 2, well, channel 2 is in the toilet.
Yeah, not so good.
Not so good, right? How about channel 3? Well, that's better.
A little, yeah.
It's better. And then channel 4 is worse. So now you got a company who makes this cable. Now, this could be a bad channel over here, right?
Yeah.
For channel 2. But this is where the performance comes. So a cable company is going to have to make they put them up to 3,000 meters at a clip for MOQs, for their minimum order requirements, right? So they're pissing these cables out like crazy.
Yeah.
Well, what happens? They're easily going to be a 10% differential just on the manufacturability of these things. So the bigger that mass margin is, the better you are eliminating the fact that you're not going to make the higher data rate, right? And everybody wants the higher data rate because they want to have all the features and benefits of 2.1.
Sure.
Even though right now they're only going to 40 gigs, one day they're going to need that, and especially if they're pre-constructing for a home, because next year we can have that interface.
Yeah, sure.
And you don't want to, you want the customers to have it all. So here's a perfect example of what happens with product like this. Here's another one. So look at this one. This is an AOC.
Oh,
yes. This one here came through. I tell you, I couldn't believe it. I couldn't believe it. It's a fiber optic cable, and this is a 12G. Now at 6G, it does good, but at 12G, so I told the customer, I said, you know what? I think they sold you 6G material.
Yeah.
And they said no. And then I guess we'll find out, because needless to say, they're going to return the product.
It's just, man, what a waste of time.
Oh, I know. I mean, it's just amazing. We see this all day long, Jason.
I'm sure.
Oh God, here's another one. So here's a good one, right?
Ooh,
So
that was pretty.
I took one single piece, but now you notice the mask. Here's the margin.
Yeah.
It's not that, so why didn't it get bigger? It's because this ISI trace came squeezing down.
You can see that one line.
Yeah, and this is where the sparkles come. When you get down to start seeing sparkles, it's because these little things start colliding with the mask, and they have little bit errors, and the bit errors are basically pixels that are going on and off. So it's and that gives you an idea what that's like. So that's actually a very good eye, except for that one trace.
Yeah.
The only problem is you can do this trace 40 times, you look at the same thing.
Yeah.
Yeah, it always will. And then this one here, okay, now that's better. Okay, so a little bit
Oh,
less
yeah.
ISI, but better margins. So you can see all of these different cables have different performance values.
Mhm.
And it all depends on the manufacturability, the cable size, the type of material they're using, the distance. It all has to do with that. So no, cables are not the same by
Mhm.
any means. I could show you 10,000 of them right here.
Yeah. Yeah.
Where I can show you, pick 5 and I'll show you they're all different.
Right.
And they may say, yeah, but you don't need it all. Yes, you do. You need all of it
Mhm.
because you're gonna have that one instance where that particular TV, or that particular source, we've been through this, Jason, so many
Yes.
times.
Yes.
And
Yes.
and but now, HDMI, look at the beautiful one. Is that
Ooh,
not beautiful? Oh, you
that's the
know
one.
who?
That's the one you
That's a
want.
yeah. That's a very special AOC. I want to tell you.
Yeah.
You get my point?
Yeah. Yeah.
Okay.
I'm
All right.
with you.
Great.
I'm with you. Yeah, we're here. We're here.
But look at that margin.
Yeah. I mean,
That, that
that's beautiful.
that's incredible.
Yeah.
So now Rev 2.0 is dead.
Yes, it is. That's a big talking point right now, is that it's gone.
This we've already had too much going on inside 2.1. We have
Mhm.
all these different resolutions. We have all these different ways of doing things. We have compression now in there if we want it. And you got cables that have to work all through these things. And then they open the rules up and they say, oh yeah, but as long as you're within the 2.0, 2.1 range, you could be considered 2.1. So that means anybody who's at 32 gigs, they're considered 2.1.
Yep. Yep.
Anybody considered 24 gigs, they could be a 2.1. Well, let's go back to your question earlier. So now, does this make it easier? Hell no, it makes it worse.
Yeah, that's
And these are some things to consider. Now look at this. They actually now make codes. See this
yep.
4K 100A,
Yep.
B? They've come out with all these different codes to
Mhm.
help the consumer.
And we, by the way, on the Murideo website, we have a data rate calculator that has a lot of
Oh,
this same information.
nice.
And I'm sorry, not the data rate calculator, the data rate chart for bandwidth. So,
Yeah.
and I remember when I first started seeing those A's and B's, and I was like, oh God, it's like,
Oh yeah. Now,
no,
now and because it's you got to match this stuff up
right?
because this hardware, it's up to the manufacturer what they want to do. They can do anything they want.
Do
So if
whatever
the
they want.
manufacturer wants to clean something, that means you got to make sure you have a source or that's going to match this thing. If the customer wants to have X, Y, Z, you have to make
Mhm.
sure they want to make sure both support it. I mean, it's not going to be easy.
Right.
I mean, this is a blunder. Now
Hmm.
they go ahead and bring 2.0 in. Well, what happens, right? Here's the point. What happens to the cables that made with low clock performance? Okay, and the cables that are made with good clock performance, you know what? You're right. They could be 24G.
Yeah.
I mean, it doesn't matter if it's FRL or TMDS. The
Doesn't matter.
copper doesn't care.
Right.
So,
Right.
you could take good 18G product and very likely use it for 24.
Sure.
All right. So you're into 2.1 at 24. Look at the confusion here. So
Yeah,
you can have
it's
some
worse.
18Gs that will work and some won't. And you know what's going to happen. I know it's going to happen. The marketing is going to go out there and say 18G and will work under 2.1.
Yeah. Right. Right. Right.
I
Right.
can see it already. This is
Yeah.
just the same old baloney, So that's what I'm most concerned about is what you're seeing right there.
The
And so now,
the one thing I just want to touch on super quick,
yeah.
they shall remain nameless. Very good company that's been around for a really long time, but I have some of the cables still that I'm not using in my own system. So they're just in a, in a closet in a bin somewhere, just as
Yeah,
backups or whatever. But
yeah,
when we started testing for 40 and 48 gigs, I was like, I know these cables are from like 2010, but man, sure enough,
yeah.
passed. And they were very expensive cables in their day. They're not made anymore,
Mhm.
but
Yep,
it was very impressive to see that old of a cable pass, no problem.
yep. We see that here a lot. In fact, sometimes, for instance, excuse me, for instance, in the old S7 days, for the active cables,
Hmm.
they finally got smart because in the earlier days of those active devices, there were only 3 channels, and they
Hmm.
bypassed the clock. But in the 8181 series on the S7 side, they went into 4 active channels,
Mhm.
And so now we just did a test on a series of products this week that made that, and of course all of those are doing 6 gigs a channel.
Yeah.
So they're getting, so through 12 meters of copper, they're getting 24G.
At what distance?
12 and a half meters
Yeah, that's awesome.
for 28G. That's 24G. That's great.
Yeah.
So I mean, it's not like it's not magic. It's because we had 18 because we had 3. Now we got
Right.
4 channels at 6.
Right.
No rocket science there, right? It's very easy. But so under 2.0, if you look at this picture now, it basically goes to this now.
Yep.
All right. So now if you have a 2.0 that had a fat clock, right? Well, then we have a nice fat clock channel 3.
Mhm.
And that's how it gets better. But this all now falls under 2.1a, and
Mhm.
this is where a ton of confusion, in my opinion, is going to take place. So we believe this revision will cause more FUD,
Mhm.
all right, than ever before.
Mhm.
And we're just getting ready for. We're already getting it. We're already seeing it. We're getting calls all the time.
Sure. Sure.
And of course, performance of the cable is going to matter because the further out they go, the tougher they're going to be. And let me
Mhm.
tell you something. When you saw those waveforms earlier, consistency.
Yes.
You
Yes.
need consistency. That's why when cables come in, we get them in groups of 3,
Mhm.
and at least we get an idea of the playing field.
Sure.
And even that, gee, you know,
What
it's so disappointing.
what are the chances? I actually took a call on this a couple weeks ago. Um, the cable would pass the cable test through the Murideo gear, but it was real finicky when he tried to use that same cable in the system.
Hmm.
So is there a chance that there's enough tolerance in that clock channel to where sometimes it'll pass and sometimes it won't?
There's definitely thresholds on again. Remember, it's analog, right?
Right.
There's definitely a certain threshold it has to meet. But generally, when that happens, because I know what you mean, you have to remember that the Murideo, um, um, they're hovering on rail. You know what that means?
We talked about that last time, but maybe just remind
There we
everybody.
Okay. So they hover at rail. What I mean by rail is that in when you're generating any kind of data, especially if you're trying to amplify any kind of data,
Mhm.
um, there's an ultimate high and there's an ultimate low. Okay. And that could be called amplitude in some cases. It could be high rail, which means
Mhm.
a high rail or a low rail. So you have 2 rails, right? You got a high
Mhm.
and a low. And so it can vary between this and this. Well, HDMI's got a certain high rail, a rated high rail that
Mhm.
they want source products. They want these source products to be at, because if we don't have this high rail, by the time it goes through copper, and then we're through the worst case cable that they use,
Mhm.
um, this rail is going to get smaller and smaller and smaller and smaller and smaller, and they
Yep.
want it to be no less than 100 by the time it gets to the destination.
Mhm.
So the rail is important. Well, the Meridios are at full rail. They're not like buying a Sony Blu-ray player. They're never at
Right.
full rail.
Right.
And they're distorted. They look awful. But you look at a Meridio's output, it's at full rail and it's perfectly symmetrical. So
Mhm.
it's kind of cheating in a way, because the Meridio has a perfect output and a perfect I squared C. I think it's down. When I measured that thing, um, I think it was less than 80 nanoseconds.
And I'm sorry, did you say before 100 was kind of or was that, sorry, was that a different?
No, that's a different subject. That's
Yeah.
that's a
Okay.
test on a cable. But so look at this way. We have 1,000 we can deal with on I squared C. That's
Mhm.
our limit, right?
Right.
Anything below that is good, right? So, but in this case, the lower it is, the better it is.
Mhm.
So as we get down, 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 and down in time, and so that's why we're usually staying in the nanosecond area, because
Right.
we're always under 1 microsecond. So when you get down to nanosecond, a short cable, usually 2, 3, 400 nanoseconds. But you got to have a source that has almost nothing to
Right.
start with, right?
Sure.
And
Sure.
you never get that. There's stray capacitance all over the place, and you can't get rid of it. I mean, you can't. But my point is that when we actually measured the rise time on the radio, it was like 10.
Yeah.
It was like non-existent.
Right.
So
Right.
so again, though, that's really almost a perfect scenario. So when you go out in the field and you start testing with that, right? You're assuming you're operating at full rail,
Hmm.
and sometimes the Blu-ray player won't work, or sometimes I know what you mean, because this is where you're good. You're damned if you did it right, and you're damned if you did it wrong.
Yeah.
And if you did it wrong, well, then that wouldn't be fair, because you wouldn't be doing what the spec called for.
Right.
What you did was the right move. So, but yeah, that happens all the time. And the other thing is that devices like televisions and the sources and things, they have their own issues. With boards, we talked about that a
Sure.
couple of
Sure.
shows back. They have their own issues with capacitive loading issues. And then they've got then you got the human side, because the human side, they can program those receiver parts any way they want.
Sure.
They don't follow a script. I mean, there may be a little one, but not really a solid script. They just write
Yeah.
that machine language, usually in C++, and they just write the code the way they feel it should be done. Well, sometimes another guy didn't think
Yeah.
that way,
Yeah.
and so it's it's a miracle it works as good as it does. To tell the truth,
Yeah. Yeah.
in my opinion. Again, that's my opinion.
Yeah.
So,
Sure.
but anyway, that's what we believe is this whole thing is going to get worse, not better,
Yeah.
and we're already seeing it. So think about those performances. Think about those relationships that we talked about today with cables, because
Mhm.
it's the same thing but different.
Yeah.
And you can have
Um,
the same thing, but
there has to be some light at the end of the tunnel, and I'm assuming that's a situation where all the stars are aligned. The source is good, the cable's
yeah,
good, the TV's good.
yeah.
And especially from what we'll just call your major brands, are you starting to see improvements in those, or are they about the same? What are you seeing on the consumer electronics products?
But we don't see that many. We do mostly transmission lines.
Oh, okay.
So
Okay.
we don't see that many, because we see a few.
Yeah.
And they're getting better. The Dead on Marantz team guys, those guys are doing better. Um, they have a lot of features and benefits in there that are kind of cool, but
Yeah.
from strictly integrity bit, from the integrity side, they're better. I think that we're seeing, uh, and this is why the cable has to be so good, because we don't know what we've got from end to end as far
Hmm.
as electronics are concerned, and the cable can be the limiting factor if it's not good, because
Sure.
it just adds to the performance problems. And so you just don't know, and they change them so quickly.
Yeah,
These models are always being changed.
it's like where are they going to get the parts from next month? Well, whoever's selling them the least
Yeah,
expensive, so it's like you
yeah.
might have
Well,
a model year run and the internal components are slightly different, halfway through the run or something, right?
yeah. They usually tend to work under ASICs, where these parts are made, and they just work. There's so few parts today. I mean, before, in the older days, we had to use resistors, capacitors, inductors, and all kinds of stuff, right?
Hmm.
Whereas today, you can make all that up in FPGA,
Yeah,
or
right.
and then you can get the chips, where they just program out and you just write code. So,
Hmm.
I mean, I'm working on an amplifier, an audio amplifier, and it's basically chipsets. There's no
Yeah,
there's no uh, there's no resistors, no
yeah,
capacitors, and it's fully differential.
yeah,
Meaning it's using plus minus splice, and it's just a toy. It's just something I'm trying out. But
yeah,
my point is that silicon technology has gone so far, and it really does. It is, these chipsets are very, very good to have. However, you don't find it's you don't find replacements for them that easy. So
right.
in other words, if you make a TV set, you make it for this particular chipset, they'll stick with that.
Yeah.
Unless it's something off the shelf, like an I2C accelerator from
Hmm.
Philips, and now TI makes it. So they can
Hmm.
get them from TI or Philips and then put those in. Transistors, if they need them, they're a dime a dozen, But when you get into these specialized parts, they're pretty specialized, and then sometimes they just say, okay, we need that one and that one. Let's change the model.
Yeah.
We'll come up with a new model, and they do it overnight. I mean, it's
Right.
amazing. They do it
Yeah.
overnight.
Yeah. The
So,
I was fascinated. I saw a video a little while ago on how they make the silicon wafers.
oh sure, yeah,
And
yeah.
whatever I was watching, they were saying it's like, it's this I mean, these things are microscopic. It's an unbelievable feat. I feel like as humans that we've been able to make something like that. What they were talking about in that video, the machine to make the wafers was like $130 million. I mean,
Oh
it's
yeah, oh yeah,
nuts.
oh yeah, yeah. And
Yeah.
they got to put it in a building. I mean,
Yeah.
it takes a whole building. It's I've seen these, and they're massive machines. They make these little teeny parts,
And they move
and
so fast. Like while
and they
they're,
move.
I mean, it's wild.
Oh, quantity is everything in that business.
Yeah.
If they don't
Yeah.
if they don't sell a lot of those things, they lose their shirt. So
Yeah.
you can imagine how tough that business model must be.
The
Oh
initial
boy,
investment, yikes.
I mean, yeah, it's you're right, you're right. So
Well,
um,
people wonder why these facilities are $2.5 billion, and it's like, well, there's one machine that's 130 million right there, and that's like
oh yeah,
on one floor of a,
oh,
like it's just, it's
it's
wild, man.
it's really mind-boggling when you start seeing some of these things,
Yeah.
and they're gonna it's just gonna get better, worse, better, worse. But I mean, I just you follow what Musk is doing. You never know what's going to happen next.
Yeah, exactly, exactly. Well, guys, if you have any questions, we do
So
have a couple minutes
anyway,
left. I don't know, Jeff, if you have
okay.
any more slides you want to show,
Yeah,
or
I just want to make sure to
yeah,
tell everybody to keep
yeah,
climbing that HDMI mountain,
sure,
and
little guy.
when you get up there, we'll see you at the top of your success. And we want questions.
I love
I
it.
like
That's very.
I like my little cartoon. So yeah,
Hey,
if
look,
you have
man,
any
I love it.
questions, let's do it.
Yeah, guys, and if you have any questions here, we do have, like I said, a couple minutes left. And I'm actually not seeing any at the moment, so that's cool. If
That's
you guys
great.
do have some questions, down the road, or maybe you watch this replay later and you think of some questions, I'm super easy to find, jason@murideo.com. Feel free to send me those questions. I'll get them over to Jeff, and between the two of us, I'm sure we can get those questions answered. So
Yeah,
I don't have
don't
anything else. This was
yeah.
fun. This was informative, and I think as things progress, I mean, I know we're still pretty early with this format, but as things progress and we do start getting really deep into those A and B labels with compression versus no compression, it's I think that you and I are going to have a job for a very long time.
Well, we've got a ton of products coming in now, and our
Yeah.
next president. I'm just trying to think what we want to do next time. There's so much material
Well, I'll tell
that we
you
can
what.
share.
Rather than you or I kind of coming up with what we should do next, I would leave it to the people who are
Let's
watching and
do that.
listening. I mean, what do you want to know? What do you want to know
That's a
about
great idea.
HDMI and cables and
That's a
inputs and
great idea.
outputs and
I mean,
testing? So
whether it be test related or some other invited guest that has expertise in that particular field. So
super cool.
there's a lot there. So
Yeah, and
great show.
I'm open to it, guys. Send me those requests, send me those questions. Like I said, if nothing is really, off limits here, if you have any, even if you want to go super geeky and super technical, I'm sure Jeff has a lot of that stuff
I
that we
got I
can
got it all. I got
that
it
we
all.
could, yeah, we can go super crazy and go super deep if you want. But if there are any, sort of high level things, and I know a lot of the people who watch these are typically installers, but maybe you can take some of these concepts and we can maybe even simplify them a little bit for maybe some salespeople or maybe people who are new at this. Like I said, man, nothing's off limits. So if you have any questions about today's session, or you want to make some suggestions for future sessions, again, jason@murideo.com. Jeff, thank you. Always
You
fun.
bet. Take care, guys.
All right, we'll see you next time.
All right. Bye bye.
Bye.